On October 24, 2003, the fastest passenger jet ever built made its final landing, and supersonic commercial flight died with it. 2 decades later, a prototype dropped from a Chinese military transport over the Gobi Desert reached Mach 6.56, more than 3 times Concorde's cruise speed. But speed was never the reason Concorde failed. And that distinction may be the only thing that matters in the race to replace it. Concorde entered commercial service in January 1976, promising to redefine air travel with a cruise speed of Mach 2.04, over twice the velocity of the fastest subsonic jets. Its slender delta wing and Olympus 593 engines allowed a transatlantic crossing in just 3.5 hours, a feat unmatched in passenger aviation. Yet beneath the glamour, the numbers told a different story. Concorde carried between 92 and 100 passengers, less than a quarter of a Boeing 747's capacity, while burning roughly 5 tons of fuel per hour. A single New York to London flight consumed about 25 tons of kerosene, with per-seat fuel use nearly double that of a wide-body jet. Ticket prices soared, often exceeding $10,000 for a round trip in early 2000s dollars, restricting the market to a narrow band of luxury travelers and business executives. The technology had delivered on speed, but never on sustainable economics. Operational economics proved relentless. The aircraft's range was limited by fuel load, and sonic boom regulations barred overland routes, confining Concorde mostly to oceanic corridors. Maintenance costs were high, and each sortie demanded meticulous inspection of heat-stressed parts. The crash of Air France Flight 4590 in July 2000, which claimed 113 lives, led to a temporary grounding and intensified scrutiny. Even after upgrades, the fleet never fully regained public confidence. On October 24, 2003, after 27 years of service and just 2,650 flights, Concorde touched down for the last time. The central lesson: achieving extreme velocity is only half the equation. Making it practical, safe, and profitable for real-world passenger service remains the defining challenge. The Soviet Union's answer to Concorde, the Tupolev Tu-144, first took to the skies on December 31, 1968, beating its Western rival by 2 months. Yet this technical coup did not translate into a lasting presence in commercial aviation. The Tu-144's passenger service began in December 1975, but regular operations lasted less than a year, with scheduled flights ending by June 1978. The aircraft's reputation was undermined by chronic reliability problems, including a fatal crash at the 1973 Paris Air Show, and another during a routine Aeroflot flight in May 1978. Most service variants carried only 70 to 80 passengers, despite a nominal capacity of 120 due to weight and balance limitations. Operating at Mach 2.15, the Tu-144's 6 NK-144 turbojets required continuous afterburner, driving fuel consumption even higher than Concorde's, and compounding maintenance demands. Frequent technical failures led to routine flight cancellations and costly repairs, while the aircraft's limited range, noise, and lack of commercial routes outside the Soviet bloc further restricted its appeal. In total, the Tu-144 completed only about 55 scheduled passenger flights before being withdrawn from service. Its short-lived commercial life and persistent technical setbacks echoed the same hard reality faced by Concorde. Breaking the sound barrier was possible, but sustaining a reliable, economically viable supersonic service proved out of reach for both East and West. Aerodynamic heating at hypersonic speeds transforms the design problem from one of mere strength to one of survival. At Mach 6, the air compressed at the nose and leading edges reaches stagnation temperatures around 2,500 degrees Celsius, hotter than molten steel. For reference, aluminum softens below 300 degrees, and even titanium begins to lose structural integrity at roughly 700 degrees. The classic alloys that built Concorde and the Tu-144 would simply melt or deform under these conditions. The heat flux, described by the Fay-Riddell equation, rises non-linearly with speed, so a modest jump in Mach number can double or triple the thermal load. Surface heat flux on a hypersonic vehicle can exceed 1.8 megawatts per square meter, as measured in recent wind tunnel campaigns. This level of energy turns the outer skin into a plasma generator, stripping electrons and creating a sheath that blocks most radio signals, a phenomenon known as plasma blackout. To keep the passenger cabin habitable, designers must minimize fuselage cross-section, squeezing interior volume and forcing difficult trade-offs between comfort, safety, and survivability. The result is a fundamental barrier. Without advanced thermal protection systems, even the boldest hypersonic concepts cannot safely carry people at scale. In March 2004, NASA's X-43A set a benchmark that still stands as the high watermark for air-breathing hypersonic flight. The test vehicle, no larger than a surfboard, was carried aloft under the wing of a B-52 bomber, then released and boosted to speed by a Pegasus rocket. After separation at around 30 kilometers altitude, the X-43A's scramjet engine ignited for a brief, controlled burn, just 10 seconds, propelling the craft to Mach 9.6, nearly 7,000 miles per hour. The entire mission was unmanned and fully expendable. Once the scramjet exhausted its fuel, the vehicle tumbled into the Pacific, never intended for recovery. This achievement proved that scramjet propulsion could deliver sustained thrust at true hypersonic speeds, but it also underscored the gulf between experimental records and real-world passenger transport. The X-43A could not be reused, carried no people, and survived only seconds in the harshest thermal environment. The leap from this kind of demonstration to a viable, crew-rated airliner is measured not just in Mach numbers, but in orders of magnitude of complexity, durability, and economic feasibility. At the heart of China's hypersonic ambitions stands a single, meticulously documented flight, the August 31, 2021 test of the hypersonic transport prototype 01 at Jiuquan Satellite Launch Center. The vehicle, designed under the direction of Kui Kai at the Institute of Mechanics, Chinese Academy of Sciences, embodies nearly a decade of stepwise engineering. The prototype's defining feature, a high-pressure capturing wing known as the Cape Wing, was first validated in a series of wind tunnel trials at the Beijing Aerodynamic Test Facility between April 2019 and September 2020. These runs, using a 1:10 scale model, measured a lift coefficient of 0.38 and a drag coefficient of 0.11 at Mach 6, with a pressure rise at the inlet of 2.1 bar. The data confirmed both the predicted lift-to-drag ratio of 3.5 and the Cape Wing's effectiveness in pre-compressing incoming air. The 2021 flight began with an airdrop from a modified Y-20 transport at 12 kilometers altitude. After release, a solid rocket booster accelerated the prototype to Mach 3, where the dual-mode scramjet took over. The craft sustained powered flight for approximately 20 minutes, reaching a peak speed of Mach 6.56 and an apogee of 30 kilometers. Throughout the flight, real-time telemetry, including speed, altitude, pressure, and temperature, was streamed to ground stations and archived by the National Center for Flight Data. The mission concluded with a parachute-aided recovery in the desert, and post-flight analysis was summarized in a technical bulletin released by the Chinese Academy of Sciences in December 2024. Kui Kai, speaking in the official release, stated, "There are still many challenges we must overcome, particularly in areas such as propulsion, materials, and structural integrity. What we have accomplished so far is just a small step in a much larger journey." The test offers concrete proof that a wide fuselage, Cape Wing configuration can survive sustained hypersonic cruise. However, the scalability of the design and its translation to a passenger-carrying airliner remain open questions, with key propulsion and materials data still classified. The evidence, while substantial, draws a clear line between experimental achievement and the realities of commercial viability. China's hypersonic ambitions do not stand alone. Around the world, multiple programs are racing to cross the threshold from record-setting flights to practical passenger service. In China, the Yongxing demonstrator completed a Mach 4 flight on October 26, 2024, powered by a Jindu 400 pulse detonation ramjet. The test, tracked by telemetry from the Beijing Aerospace Command Center, lasted nearly 3 minutes and reached altitudes of about 15 kilometers. The Jindu program itself has published concepts for vehicles targeting Mach 5 to 6 cruise, with laboratory tests showing peak thrusts of 25 kilonewtons in controlled conditions. In December 2023, the Beijing Power Machinery Institute released data on a rotating detonation engine, reporting continuous thrust at Mach 2.5 and exhaust temperatures above 3,000 degrees Celsius, a promising step, but still far from integration with a passenger airframe. Western efforts are pursuing a different path. Boom Supersonic's Overture, for example, is designed for Mach 2.2 transatlantic service, with a first flight planned for 2027. The X-59 project, led by NASA and Lockheed Martin, focuses on reducing sonic boom for overland supersonic travel, not hypersonic speeds. These programs are primarily aimed at regulatory acceptance and operational economics, rather than breaking into the Mach 5+ regime. Despite these advances, the pathway to commercial hypersonic flight remains filled with unknowns. No program, Chinese or Western, has yet demonstrated a reusable, certifiable propulsion system for sustained cruise above Mach 5. Materials capable of withstanding 2,500 degrees Celsius for extended periods are still in early testing. Regulatory authorities have not defined certification standards for hypersonic passenger aircraft, and airport infrastructure remains unprepared for the demands of such vehicles. Kui Kai summed up the state of the field. There are still many challenges we must overcome, particularly in areas such as propulsion, materials, and structural integrity. What we have accomplished so far is just a small step in a much larger journey. The race is very much alive, but the finish line, true commercial viability, remains out of sight. Hypersonic flight now exceeds Mach 5, but the gap between technical achievement and commercial viability remains vast. As Kui Kai notes, what we have accomplished so far is just a small step in a much larger journey. The real test isn't speed, it's making speed sustainable, safe, and accessible.